Uniform solid disk. Calculate the moment of inertia of a uniform solid disk with mass capital M and radius capital R for an axis perpendicular to the plane of the disk and passing through its center. So here is our disk. If we are at a distance lowercase letter r from the center, we have, for a small variation in the angle theta in the counterclockwise direction d theta, an arc length of r d theta, and a small change in the radial position of dr will basically approximately give us this rectangular region with area r dr d theta, and that will have a mass dm, so that will be our mass elements. So this a solid disk is a two-dimensional object, so we can talk about the mass density as areal mass density. The mass density sigma will be equal to, because it's a uniform mass distribution, capital M total mass divided by the total area pi capital R square, so that the mass element will have a mass sigma multiplied by its area dA. So this will be equal to sigma r dr d theta, provided that we have this area r dr d theta and mass density sigma. So to calculate the moment of inertia with respect to the z-axis, that's an axis perpendicular to the plane passing through its center, this is integral r square dm. Now we have two variables to integrate on, theta and r, using polar coordinates. So integral is a double integral. R square is the distance between this mass element and the rotation axis, and then we have dm sigma r dr d theta, and the limits of the integration will be, if I go from theta equals 0 to theta equals 2 pi, I will be exhausting the whole space here, provided that r also goes from 0 to capital R. So 0 to 2 pi, integral 0 to capital R, sigma, now r squared times r will be r cube dr d theta. So we will find that this is sigma times, if we perform the r integration, it will be r to 4 over 4 evaluated between capital R and 0, and the theta integration, because there is no theta anywhere else, will give us just delta theta, which is 2 pi. So this will be sigma times pi r to the 4 divided by 2. Now we can substitute for sigma our uniform areal mass density, capital M divided by pi capital R square multiplied with pi capital R to the 4th power divided by 2. So this will give us, pi r square will make pi r to the 4 r square. The final answer will be capital M capital R square divided by 2. So let's put our final answer in a box. Alright, so we are trying to calculate the moment of inertia with respect to the center of mass of a uniform solid disk, mass capital M, radius capital R. We identify a mass element dm at an angular location theta and radial position r with respect to the center of mass. Its mass will be its area multiplied by the mass density, where the mass density for a uniform mass distribution is capital M divided by pi r squared. So it will be sigma dA. Now, what is the area of this element? If we have a small variation of the angle d theta, we will have an arc length r d theta. And if we have a small variation in the radial vector here, this will be dr. R dr d theta will be approximately the area of this element in the limit dr and d theta goes to 0. This is more and more turning into a rectangle. And this integral r squared dm will be r squared times sigma dA, which is sigma r dr d theta. So that is sigma r cubed dr d theta, where we have to go from theta equals 0 to theta equals 2 pi for all possible radial distances from 0 to capital R. The integration gives us r to 4 over 4 between 0 and capital R. And the d theta integration gives us just the change in the angle, 0 to 2 pi, which is 2 pi. And when we substitute for sigma, capital M over pi r squared, we obtain the final answer, capital M r squared over 2.